A good follow-up from last week's linked list because we are going to build these using linked lists. Don't worry if you weren't here for linked lists, it's not going to matter too much. But, so let's talk, what are we talking about first, queues or stacks, Jenny?
Queues.
All right, queues. Queues. Anybody know the acronym?
Acronym for queue? A line?
Well, is it?
First in, first out.
Ah, that's really good. You did great. You got it right there. FIFO. FIFO. Okay, so queue. Think grocery store line, right? If you're the first person that gets in line, you're the first person that checks out, right? Everybody that comes in behind you just stacks up, and as the first person leaves, that next guy is the first person. He goes, so on and so forth, right? First in, first out. So just think about circles, right? Actually, let's do our thing like last week. So, because it's linked list built the exact same way. You got like a value, well, you don't have to have a value, but whatever your node is, and a pointer to the next node, right? So, we're going to do circles this week. Circle. So value and in. And this one points to this one. This one points to this one. This one points to this one, right? So when we DQ this node, DQ, get rid of it, and all we have to do to DQ it is just remove that thing. Now this one is the next one in line, so we DQ, DQ. Now, kind of important on this structure is why you don't just, oh, well, why wouldn't I just use a list, right? A regular list, then I can jump around the list as I want. But think about what this data structure is used for. Say you have customers, right? You're processing online orders, right? You don't want to just be able to hop down through and everybody grab whatever they want or whatever, right? Like, no, first person that comes in gets checked out and so on and so forth, right? You're doing this online, you are dequeuing and you are in-queuing. In-queuing just means sticking on the end, right? This one, oh, got another one. And again, same thing with linked lists. The reason that these are important over, say, arrays or something like that is because you don't know how many of these you're going to have or how often this is going to change or any of that. But with linked lists, because you're just creating them as you go, you can, and pointing them to end, they can literally be anywhere, right? Anywhere in the heap, every class you make, just as long as it points to the last one. This thing is going to DQ, 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 InQ, 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 right? Pretty simple, right? You've got a data structure there. Nice and easy. So DQ means to get rid of it. InQ means to put it on the end. And it's constantly rotating like that. Very simple stuff. I will say, just same thing with stack too. One differentiation that some languages do is when you DQ, so you also have something called a peak, right? And all that means is what's the value on this first one? What's the value, right? So you can just look at it, right? Some languages, C++, at least the last time that I looked at it, when you DQ something, it does not return that node. You have to peak if you want that value, and then if you want to get rid of your DQ. Most languages, modern languages, C#, Java, quite a few others, when you DQ it, it just returns that node as well. So if you want to DQ it and then process the information on that, you can. That makes a lot more sense to me, but you know, I can see it both ways. Like, you know, the structure is there. Like, no, DQ is only for DQing this, and peaking is only for peaking. So here and there, I like being able to just DQ stuff as you go and take a look at it. So everybody got this? Remember linked list, pointing, great thing about linked lists, create an object, throw it out in the heap, doesn't matter where it goes, doesn't matter how big it is, nothing, just as long as that pointer points to the next one in line and you maintain that chain. We will look at some code for that as well. We're going to do stacks first, just because they are quite similar, just different rules. All right, so first in, first out. Jen did that. That's all. Nobody saw nothing. All right. First in, first out. So we're going to talk about stacks now. Anybody want to guess?
Last in, first out.
Ah! Last in, first out. Easiest analogy for stack of plates, right? You wash your dishes, put your plates up, right? Just put them on top. Well, you can't get to the bottom plate. Anybody that's ever tried knows that makes a lot of racket, right? Trying to pull that last thumb. Can't do that. All you can do is get the top one. All you can do. Perfect. And all you can do whenever you get done is put them on the top. You can't stick them in the middle. You can't, right? Always from the top, always from the top. So, same thing. That I'm going to do this just because top sounds more. So, yeah. You got your stuff, points to the top. Points up, points up, points up. You can only ever put a node on the top, right? Notice I just built that up, right? You couldn't say, oh, well, I want to put a node in here. Nope. Break stack rules. Can't do it. Shouldn't even have a function to do it. So, last in, first out, meaning you only have access to the top. You get down with this one, well, now this is push and pop. So, push one on, goes to the top. Pop one off, takes off the top, right? Can't ever touch this one down here without popping all of these off. Now, Jenny, I mentioned stack, which by the way, stack as a data structure, while it does the same thing as the stack that you hear referred to in computer stuff is computer programming. It works, it is a stack, but it is the stack for your computer. Works exactly the same way. So, I'll give you an example of this. And this works for every function and every operation that you do in your computer. Is you put something out there, throws it on the stack. If it needs to make a call, it does not get returned until it gets back down. Easiest example of this is like the old tried and true Pedmans, right? So if you have 1 plus, let's say 1 plus 5, and minus 2, right? So in fact, let's go ahead and add another one on there just to make things interesting. Let's see, we'll do 1 here and do plus 1 just for ease. So your computer comes in and says, hey, I got all this stuff with parentheses and I need to process this in the correct order, right? So what it does, it takes all this and throws it on the stack. And then it says, oh, but I have a parentheses here. So I actually need to throw this one up on the stack and solve that first. And then I see I have another one in here. Let's come off. So I need to actually pop this on as well and solve this first. So you notice we have a stack, right? And it says, the computer says, well, I have to solve these in order of the stack. Everything, every program, every method you've ever ran, everything. Do it on the stack. So it says, all right, well, this is 6, right? So it comes down and says, all right, now I've got this. Do this. Now I solve this because, again, until I get off the stack, I can't do anything, right? Solve this. All right, so now I've got 4. And then I've got all this. Pop this off, and I come down, and I've got this down here, and then I return my end, right? 4, which is, again, 6. So that's stack, right? So same thing with computers. Recursion actually, exact same way, is when it calls that method, those on the stack. If there's another call in there, because it can't return until that one inside of it does, throws that one on the stack, and throws that one on the stack, and so on and so forth. And so as that stacks up, it can't return that last one. In fact, that's why if you add, like say add a number or whatever, it will pop out and it'll be in reverse order, right? Because that return is actually from the very top of that stack. That's recursion. But, I made that sound easy. Again, every recursive function I've ever written, I had to write it out on paper first because it sounds really easy, but what's really going on each time this thing gets called? So it does get confusing, but all of that works on the stack. And by the way, because that works on the stack, you will see, wow, this is kind of getting off in a different topic, but there are reasons to do things on the stack, because if you stack that up, that when that returns, that's very fast, right? There's no, well, process this, and then process this, and then process this. It's throw it all on there, and it's all processed, and then your return is like instant. So there's, now the downside is, of course, is the stack has very limited memory, so if you just tried to load up, that's when you get stack overflow, right? Boom, everything explodes, very small amount. So yeah, there's the plus to using stack, and using heap, of course, is on whatever your amount of memory is. That's a good thing, right? So again, you see a benefit of using linked list for stuff, right? So limited function. So there you go. Now you have a stack. All right, let's look at some code. Everybody cool with both those concepts? First in, first out for queue. Last in, first out for stack. Make sense to everybody? Nope. All right. Clear this up and we'll look at some code.
Wait, what was the difference between the stack and the heap then?
Stack is a set amount of memory, so it's a fairly small, I actually used to know this number, but anyway, a very small amount of memory, and everything gets piled up on that and returned off, right? But it's a very limited amount of memory, and it's in a specific location, so it's very fast, right? Very fast access. But heap is essentially just assign me a pointer somewhere out in memory, and I can have as much as I need, and it can be anywhere. So, but then the downside to putting stuff in the heap is that obviously it's slower, right? Because now instead of going directly to some stack, place, now I'm having to go find it in the memory, so it's a little bit slower. So, but there's good size use cases for both, right? Like
I was just wondering the difference.
Sure.
Because I was unclear. I thought that it was one was first in, first out, one was last in, first
right,
out.
but so you're thinking, sorry, I didn't mean to confuse with that, Scott, but the stack is it's a data structure that your computer uses, right?
Yeah.
But they're two separate things. Like the stack that your computer uses, that you use to develop with, right? The stack, it is a stack, right?
Okay.
Right. I know the terminology. I mean, they call it a stack because it is a stack.
That's where I was getting
a little bit confusing.
So
yeah.
the old thing I learned is still correct as well. It's just not. It's an example of same words talking about different things.
Probably. All right.
What about
Get this out here.
a call stack? Is that the same thing?
Pretty much. I mean, it is an example of a stack. Yes. All right. Let me see if I can maybe get this rolling. All right, man, why is the resolution on this TV so ginormous? We'll try to play around with it. All right, so I got already coded out a bunch of stuff, but we are going to go through it kind of bit by bit. So first, you want to do queues? You want to do stacks? Are a little tiny bit easier to implement, so we'll do stacks first, and maybe even zoom in and stuff. Again, linked list. So first thing that we need, if we're going to make any kind of linked list, what do we need? Anybody? I'm going to give you a hint. That's right. That's right, a node. So pull up node and just take a look. Node, again, for example purposes, super easy, right? Just a value and a pointer to the next node, right? Same thing as last week. Again, this is all built on the same stuff. I added a couple extra constructors in here just because, in case you wanted to initialize it with a value or initialize it with, whatever. So, but same thing. Just call a node. You have a next and a value, right? All right. So we're going to create a stack. Now, same thing with the linked list, but instead of just next, what we're going to need is always reference to the top, right? Because we can only push and pop off of the top. So we need just whatever. I added some other stuff in here, just normal stuff like a count. Because when you add stuff, you obviously want to keep a lot of times you want to know how many things are in my stack, how many things are in my queue. So have a count as well. But Yeah. So top, node, and a count. So we're gonna need a couple things. We need to know, like a peak, right? Peak meaning what value is in my top node. Very simply done, right? Return whatever the value is in my top node. That make sense? We call Q the.
So if you're in a node further down, what would peak return?
You couldn't get to that. Remember, the rules, you can only hit the top. You can't look down, otherwise, why not just use a list, because then I can jump down or whatever. It is important, these data structures are important, because A, it makes sure that the rules of your data structure stay in place, right? Like, you don't have other classes that have access to the middle of your stack. That would be bad. That would be real bad, right?
So even if you did start at the top and scroll to like the 5th element and then tried to peek, you couldn't?
Nope, you can't get to the 5th element without popping the top 4 off,
Okay.
right? You always have that constraint. The only thing that you have access to in a stack is the top, nothing else. I'm going to let's do this. Let me show some. All right, so we're going to create a new stack, right? Simple code, new stack, right? Everybody? All right, and then we're going to push a new node on. New node with the value of 42. So let's take a look at push. All we got to do for push, say, okay, whatever this node is, whatever I'm sending in, right? Think of the line. Where's my thing? Think of the line. So let's say I got nothing. First round, I got nothing, right? They don't have any nodes, I don't have any lists, it's nothing, right? But I throw a node at it. Okay, well, I just want to make sure that this node that I'm passing in, that is also where the top is pointing to, right? Because no matter what, if I push a node, where does it have to be? Top, right? So no matter what, node's going to the top. And then, the next node is going to point to where the top used to be. And this is important because, all right, so now we have a node, right? Now I want to throw another node in there. So what's important to maintain that top element? I have to say, okay, well, I've got a new one, but top is pointing here. I want to make sure that top always points to the new one, so when a new node comes in, I'm going to point this node to this one, and I'm going to point top to here. And I'll do that again if I add another one. Oh, top's pointing to the wrong one, right? If we do a peek, it's going to show us this one. That's not what we want. Always has to be. So we're going to point this one here. We're going to put top up here. Every time. And so, that's what we've got here. So if we push, it says, whatever node that we're going into, point that to point its next. Remember, there's a next variable in here. Point its next down here to where the top used to be, and then set this one to the top. Those two things, all you got to do. And then we up the count, right? Because if we add a node, we want to keep track of our count. Now we up the count. Easy peasy. All right. I do have another one in here, as you can see. Just this, by the way, you can't do in some other languages. One of the beauties of encapsulation, being able to do this. I can just call push with the new node with the num. Yeah, it's glorious. You guys want to learn to love it. But anyway, all right. So pop. So we know how we can push new nodes on, right? Everybody good with that? I know David is. Look at him. Man, he's killing it back there. All right. So, what if we want to remove one? All right, that's called pop. Popping it off the top, right? So, if we want to pop, we're going to create a new node that we're going to return, right? So this is the one that we're going to pop off here. We're going to create a new one, and the reason that we're going to do a new one is because we always want the top to point to the top of the the stack, right? So if I pop this one off, no, top is now pointing to some floating node. That's no good. So pop this off, return it, and then put top to the next one down.
Do
Right?
you actually have two different stacks now?
Nope. I have one node that I've returned. I popped that off,
Mhm.
and I have the stack because top is always pointing to the top.
So now the one that you popped off belongs to.
To whatever I returned
Whatever
it
it
to.
was
You don't
that
even
you-
have. You don't have to return. I mean, you don't have to do anything with that. You can just call pop. It'll return it, but since it's not returning it to anything, it'll just disappear.
Yeah, that's what I mean, so you either pop it and return it to some other
To something,
function,
right?
or
just
to delete it.
Get rid of it, right?
Okay.
Yep. So we pop that off, set top down here. Same thing with the code. So we create a new, the reason we create a new, by the way, a new result node there is because if we just return top, it's gonna be pointing to the wrong one, right? How are we gonna do that? No, we wanna return that, and to do that, we first have to set this to the result one, and then we set top down here, so now it's not pointing to that one, then we can return where we set it to. So, popping it off, decrease count, right? Maintaining that count, up and down, that way, because we just popped one off, now our list is one less. Maintaining count, easy peasy. Alright, so let's do a couple example ones. We're gonna push on 3 numbers, right? Anybody know the importance of that first number?
Answer to everything.
That's right. All right, Scott. Bonus points for you. All right. And then now this method, by the way, is not one that's normally in anything because this full-on does break the rules and is cheating. It's just for the demo purposes. And it just spits out what the current stack is. So, I'm going to go out here real quick and make sure everything's not broken. All right, so as you can see, spits out 420, 69, 42, right? That's what's currently in our stack. Now, if we go in here and we, well, let's first log the count, make sure that we know, that what we're doing is right. Should say less than 3. All right, cool, we're winning. Now, let's go down here and pop one off. And we will run the log again and take a look. All right, so what's it going to print out? Jenny, what's it going to print out?
420 and 69.
Man, that's it. I just need to go home. You guys are already too smart.
It's actually going to print all of them, right?
That's true. And the new one, yes. All right, she's smart
I
aleck
thought
here.
420 would be at the top because we pushed 42 first and then we pushed 69. Which
So
places that at the
this
top.
list that you're seeing, it is going down the list, right? So you'd have to look at the method again. You wouldn't normally be able to do this because it's cheating, right? It's not popping them off. What it's doing is calling this method log, which simply says, okay, go to the top and print out each one below it. So ignore the order that that's in because it's not from the top, it's from the back, right? I mean, yeah, it makes sense. This is just, again, the list thing, or the log thing is just for demoing what's currently in the stack. So, all right, let's make sure that Jenny is correct. I believe she is. Oops, it's down there. There you go, 6942. So notice what I did was pop off of the top, right? Okay, and now, that's good. Also, another method that I have in there is just contains on both of them. You'll see that on most stacks and queues. Contains just basically goes through your stack or your queue and says, is whatever number I'm looking for in there, right? Like you put in 420, it's gonna say yes. So easy peasy. All right, how are we doing on time?
And for it to search that for contain, is it kind of popping off?
No,
until it finds one?
actually, that's allowed because it's not manipulating anything inside
Okay.
the thing, right? All you're saying is, does this stack somewhere in here have this thing? And, yeah, the answer's true. There's usually a few others, that you can kind of utilize just, like putting in the full list of stuff and information, things like that. But these are kind of the basics. You're always going to have this. By the way, there are reasons to write your own stacks and queues, but they're pretty solid in every language. So, like, if I was actually going to do any of this, I would just simply say queue, right? Like, new queue, whatever. I would let the .NET stuff do it for me. Same thing with any language. Don't reinvent the wheel. But this is a good example of data structure. And there's absolutely times when you wanted to do some priority queues, the perfect example, right? Like straight out the box, it's not a thing, right? You might want some queue where it's first in, first out, but what if this priority, like the third item, has way higher priority? Well, now you need to keep track of that. So if item 1 is supposed to pop off, it's next, but it's priority 1, and item 3 is priority 10, well, now we, you know what I mean? So that, you can see where that would become quite useful. If, your customers are premier customers, well, they need to have, better access or, stuff like
It's
that.
like determining who gets answered next on 911 calls.
Right, exactly. Which should always be me, but, But anyway, all right, so let's do queues. We're doing good. Redo all this. And queue. So making a new queue, very easy. Anybody want to notice my variable name there? So cute. All right, we're going to enqueue a few numbers. Very familiar numbers, right? Enqueue, same thing, right? Except for we're putting it on the end, because this is a queue, not a stack. We're putting this on the end, and we only have access to that first one. So enqueue 3, again, this is my cheat function, so just for demo purposes. We'll come down here and we have a fail. Oh,
Do you have
sorry.
something in your queue that,
I forgot to comment 2 things out. There we go. All right, cool. We got our queue, right? Sweet. Everybody good? What's going on? We are going to dequeue something. Dequeue takes it off of which side?
The first one.
Front side. It's the best. All right, let's see. All right, so the first thing that we queued up was 42, right? So that's probably what's going to get rid of? Hope so. Let's find out. I'm used to hitting F5. Boom. Done. Easy peasy. So let's just take real quick, let's take a look. Most of the functionality is very similar. Now, in a queue, you have to maintain 2 pointers because you always need to know where the first is. I named it head as well just because it's general, whatever. But you also have to know where the last is, right? Because if you add a new node, you always want to put that on the end, right? You always want to take from the front, put on the end. So you have to maintain 2 pointers. Adding it, everything is pretty much the same. Queue, stuff like the same thing with the count. We add 1, we up it, lower 1, DQ 1. But now unlike the other one, we need to know whether, because the first and the last all have to have a place, right? Like we have to check first when we add a node, because if it's blank, we need to point both of them to the same place, right? The last and the head need to point to the same one. So that's the first thing we check. Just is head null? Meaning is my list blank? If so, well, point head to the node we're passing in and point last to whatever was in there. And if not, then very simply, because, for example, stuff out here, if we have a couple, and we want to add one, we've got to come out here and we say, just very simply, okay, we have a node here, right? And we want to add it to our list. All we got to do is say, oh, this last. Now all we got to do is point that to this one, and then set last to this. That way we always know if I want to add another one. If I didn't set last to the new one coming in, and I wanted to add another one, last is still pointing up here, right? So that's all you gotta maintain. Just point to whatever the last one was to your new node and set last to that one. Boom. You have a running queue. Easy peasy. Everybody got that? Pretty simple stuff. New node, set last. Yes?
So when you set the very, very first node, and you said you're gonna change
Right.
the head, so head would become null?
Head wouldn't become null. Head just points to the same, they both point to the same
They
line.
both go to the same.
Right. Because if you have nothing and you say, okay, well, I'm starting a new queue, but you have to maintain head and last, right?
So that's first in.
Yeah, first and last. And then this always points here unless you DQ it, which we're gonna talk about in a second. But then if I have another one, now last, which is also pointing here, now we just point that here. Last. Boom, you have a queue. Sweet pickles. All right, now let's talk about dequeuing. It's also pretty simple. By the way, again, beauty of the real language, just letting you know. Just letting you know. Okay, DQ. Same thing with returning the stack, right? Except for it's not, you're returning from the head as opposed to the top. Same exact thing, but you create a new pointer just so that you can change where head is pointing and return that. You're going to set head to the next one, right? So head's currently here. You're going to get rid of this and set head to here. Again, this one goes out to whatever you returned it to, and your queue continues to run. Do-do-do-do-do-do. Awesome. Peak, same exact thing as well. All you're going to do, whatever my head is pointing to, give me that value. Don't care what it is, how long the stack is, nothing. Just whatever's the value in there, return it. And contains works the same thing as well. Goes through your queue, says, is this value in here anywhere? And if it is, returns true. Otherwise, it returns false. And if you want to see that code, by the way, again.
So is peak a C#
Nope.
method, or you
Nope.
want that?
Pretty much every language I've ever worked with that had queues, peak, push, pop,
Those
all,
exist.
or sorry, for queue, peak, queue, DQ, same thing. And then the idea is pretty simple, just
Yeah.
what's the value in the whatever node, first node